Okay. Let's get back. All right. So let's already talk about um, the how to interpret the coefficient of logistic regression, right? So unlike linear regression, which is very simply a marginal effect, right, of x, because of this transformation, the the way to interpret the coefficients of logistic regression is a little tricky, right? Okay. Now, first of all, you need to apply exponential transformation to the coefficient, and then after the transformation, it actually replies the odds ratio. It is not the incremental probability. Okay. Let me say it again. This is the, as you can see, the exponent of coefficient indicate the ratio of odds. Okay. This is in one word, very precisely. This is the way to interpret the coefficient of logistic regression. Okay. And because they are, the effect is expressed in the terms of ratio, right? So the effect multiplied rather than add to each other, right? So these are the two things that you need to know. Now that the difference between what sometimes is desirable to see the increment of probability, right? But unfortunately, there is no straightforward way to transform odds ratio into incremental probability. The transformation is kind of like pretty complicated mathematically. I do not have time to explain it for you, so I have some code, example code here for you. So if you are interested to like transform the odds ratio into incremental probability, you can follow the code and try to do it yourself. Right? It's not easy thing to do because the same odds ratio would transfer into different incremental probability, right? Because of the nonlinear transformation of log and exponent, right? So there are some complicated here, right? But as I told you many times in our course, our purpose is not to like use the coefficient I told you already, right? In order to get to verify the coefficient estimation, it take a long training, right? It take a very serious training before you can estimate the coefficient correctly, right? So in our course, we do not intend to like use the coefficient individually, right? In our course, we tend to like use the coefficient collectively to do prediction, right? Because prediction is our purpose. So we will not go into the detail into this coefficient interpretation too much, okay? So I'll stop here, right? If you are interested in how to transform odds ratio into incremental probability, you can like take this code, and if you have a question, you can come to me. We can discuss later, okay? So for now, I want to switch to the third notebook, which is dedicated for the accuracy measurement of logistic regression. As I told you, right? If we are talking about fitting a model, examining the coefficient, doing prediction, the process is basically uh, very similar, right? Logistic and linear regression. But their model accuracy, but talking about model accuracy, the measurements are very, very different. And the accuracy measurement on logistic regression has a very serious, has very important applicational implication in business analytics. Okay, let me say it again. The accuracy measurement on a binary model, a probability model, is very different from that of linear model. Okay, and they have a very, very important implication on business decision making. Okay, so in this hour, I'll try to go over the accuracy measurement, right? And in next week, we will try to use this accuracy measurement to help us make business decision. Okay, it's not straightforward at all, right? It's a little bit tricky here, right? So be careful, okay? So let's think about the accuracy measurement of linear regression first, right? There are two types of measurement, right? First thing is R squared, which means the proportion of variance explained by the model, right? Still remember that? Okay? Because we are using the model try to resolve, try to explain the variance of y, right? And if I can explain like 60% of the y's variance, then R squared will be 0.6, right? Okay, which means that compared to predicting y simply by using the average of y, okay, using this model can resolve 60% of the error, can resolve 60% of the error, right? That is one way of measuring the accuracy of a linear model, okay? And the other way of measuring correctness of linear model is to see the average error, right? So this is more straightforward, right? It's just try to give you the expected value of error, okay? It's two way to measure the linear regression. And the higher the R squared, the smaller the error, right? The relationship are like fixed relationship. The smaller error you have, the higher R squared you have. Okay, that's very. They are kind of like consistent with each other. Okay. So accuracy for linear regression, for regressors, is actually kind of easy in compare with the binary, right? So now, if we have a binary type of outcome variable, then what we means by, we have a lot of different way to measure the accuracy of a probability model, okay? And that could be very confused, okay? Let's go to Notebook 10C. What? So in the first code chunk of 10C, I do a lot of things. Right? I read in the data, split the data into training, testing, and I build a model out of the training data, right? I take a summary of 0 and 1, and then let's first of all take a look at the training data first, okay? Do prediction on the training data first. As I say that when you code predict without new data, then the predict function will actually predict the training. This is actually the predicting value of the training data itself, right? So let's go back to last one. When I do this, I will have like a vector of 99 probability, right? Because logistic regression, when you use the predict time equal to response, you will actually return the probability of each of the data point, okay? The predicted probability. So there are 99 points in the training data, right? So there are 99 predicted probability here, okay? We can see it. See, they are probability, right? So 99 probability is difficult to observe, so we kind of like do a histogram on this predicted value, right? See, because there are 99 of them, right? So I kind of like, this is called the distribution, right, of predicted probability. See that? Okay. So let's go back here. So this is the distribution of predicted probability. Okay. So if I want to like kind of like, as I say that the predictability of in the traditional way of using logistic regression is that we will have a cutoff value set at 0.5. Because whatever, if the model predicts that the probability of y equal to 1 is larger than 0.5, it is more likely to be 1, right? And the data points here are less likely to be 1. So they are more likely to be 0, isn't it? Right? So traditionally, there will be a cutoff threshold set at 0.5. Okay? So the data point here will be predicted as y equal to 1. They are more likely to be 1. Okay? And data here are more likely to be 0. Right? So the practice that I want you to to learn is that when you do the prediction, you basically predict the probability instead of predict the value of y, right? Okay? Because the linear combination cannot calculate into 0 or 1 directly, isn't it? It only calculates to the probability of y equal to 1, right? So when you do the prediction, you predict the probability, okay? And you need to cut the predicted probability, right? If the probability is larger than 0.5, you will say that, okay, this point is more likely to be 1, okay? That's the way it works, okay? And this is for training, right? For now, we need to introduce a way to measure the accuracy. Which is the confusion matrix, okay? Now, let's take the training data as an example, right? Now now I have for each point within this training data set, I already know its pool care, right? Right? Because this is training data, I know that actually the actual pool care, right? And here, if I set the threshold at 0.5, okay, I will have a prediction about each of the pool care, right? Would they be the same? I mean, for all of this point, I will predict their pool care to be 1. For this point, I will predict their pool care to be 0. But prediction cannot always be the same as the actual value, isn't it? There will be difference, right? As we already seen here. We can see it here, right? This point I will predict it because their probability is larger than 0.5, right? So I predict them. I will predict their pool care to be 1. But actually, for this 3.1, 2, 3, I make a wrong guess, right? I do a wrong prediction, right? For all of this point here, I will predict their pool care to be 0, but there are some error here, right? See? So this is the ideas of confusion matrix, okay? Because I have a data, and this is the actual value within my data, right? And according to the prediction, after I apply the cutoff of 0.5, right? I can, for every point, I can treat it as 0, predict it as 0, predict it as 1, okay? Usually, when we predict it as 1, we will say positive, okay? And when we predict it as 0, we will say like negative, okay? So this is the prediction, and this is the actual value. And actually, the 4 case could happen, right? There are 4 different cases, right? According to the combination of the actual value and the prediction value. There are 4 possible cases. And you can put that in the matrix. And this matrix is called confusion matrix. See that? Okay. Okay, so let's take a closer look at the confusion matrix. See, as I told you that we have a metric here, so if I set the cutoff value here, right? If I set the cutoff value at 0.5, okay, then I have 14 points in this side, okay? And in this 14 point, I will have 4 points, because here I will predict it as positive, right? But actually, there are 10 points, which is really actually 1, okay? But we have 4 points, they are actually 0, right? So for this 10 point, my prediction is correct. For this 4 point, my prediction are wrong, right? If I set the threshold at 0.5, okay? And in this side, I'll have like 85 points, okay? And within this 85 point, 70 point they are actually 0, right? So my prediction is correct, right? But for this 15 point, my prediction is wrong. See that? So the combination of actual and predicted value will form a matrix, okay? And within this matrix, the diagonal are the correct prediction. And the value out of the diagonal are incorrect. See that? Okay. Okay? Yes?
Why have you taken 3 thresholds?
No, I'll explain that later. That's, for now, let's take it, this threshold first. Okay. So when we set traditionally, that's the way we do it, right? We set the threshold at 0.5, and then we will have some positive, we will have some negative, and then we build the confusion matrix, okay, and then we can calculate this accuracy measurement, okay. Now the first thing is the accuracy, right? So accuracy, as you can see that in the denominator, they are actually all of the values, right? Actually, each of the cell within the matrix has a specific name, okay? This is called true negative, because we predict negative and it is actually negative, so they are true negative. And this is false negative, right? Because we predict negative, but they are actually 1, okay? Likewise, this is true positive, because we predict positive and it's actually 1. And this is false positive, right? So we have four number, right? After you do the prediction and after you cut it at the threshold, you will get this 4 number. And out of this 4 number, there are many different accuracy metrics can be calculated, right? And the first thing is, of course, accuracy, right? So accuracy is you put all of the data point, the number of data point, as denominator, and in the denominator you use this to correct, right? The fraction of correct prediction, right? That's called accuracy. Get it? Right? And then there's another. Actually, there are a lot of different, like 20, 30 different terms of accuracy measurement here. Very, very confusing, right? If you go to Wikipedia and you type confusion metric, now on the top of the page, you will see this 4 term, right, that we just defined, okay? And out of this 4 term, actually you can define so many different accuracy metrics, right? And what makes it worse is that some accuracy measurement have many different names. For example, the true positive rate is sometimes called it hit rate, sometimes called it recall, sometimes called it sensitivity, right? So they are very, very confusing, right? So don't try to remember it, okay? When you see this term, like, just look into Wikipedia. That is the only way to do that. Otherwise, it would make you very, very confused. Okay? The philosophy is actually go to the basics, right? Remember this 4 term. What is really, really important is these 4 things and the metric itself, okay? And for the rest of the things, I think you only need to remember a few like useful term is good enough, right? For example, accuracy is one of an important one. And another important one is sensibility, right? Take a look at its denominator, FNTP, which is FNTP, right? So given that you are 1, the probability that I can predict you as 1. That is called sensibility. So if you are 1, how good I can tell you that you are positive, right? That's called sensibility, right? If the test is sensitive, then for those who are 1, I can have a very high probability to tell that you are 1, isn't it, right? And, well, the specificity is actually just the reverse, okay? As you can see that the denominator is like, the denominator is actually t equal to 0. See that? Okay. So Tn at p, right? So, which means that when you are 0, I can specifically say that you are 0, right? Okay. So, well, sometimes in some applications, sensibility is more important. In some application, specificity is more important, right? Depends on your business application, right? The reason that we have so many different type of accuracy measurement is because that the probability model is used in so many different disciplines, right? And in every discipline, they have their, according to their purpose, their focus are different from each other, right? So sometimes they, you look for accuracy, sometimes you look for sensibility, sometimes you look for specificity, and they are not compatible, right? I mean that sometimes they have trade-off between each other. Okay, that is the idea about the accuracy measurement of probability model. Okay? Probability model, so you cut off, then you have probability matrix, then you can calculate this term. Right? Now back to the question that we just go to, right? Traditionally, we will set this ratio at 0.5, right? To do this measurement, okay? But in a real business environment, the ratio might not be 0.5, okay? And sometimes especially in today's business environment, a lot of data, they are like very imbalanced. For example, the click-through rate. If I'm Google, right, and I send an advertisement to you, right, I want to estimate the probability that you click on the advertisement. Right? That probability is actually lower than 1%, maybe 0.5%, something like that. Okay. So in that case, using accuracy is not a very good measurement, right? Because even if I do not have a model, I simply guess that you do not click, I will have an accuracy of 99.5, right? I mean, in case as the average click-through rate is just 0.5%, right? So if I have a dumb model that I predict everything as no click, right? Still, I will have the accuracy of 99.5, right? Isn't it? Right? So that fixed ratio type of measurement are sometimes misleading. And in the real business application, in the modern business application, where there are a lot of imbalanced data, okay, it's no longer very useful. Okay. So in today's environment, sometimes it is desirable to shift the threshold upward or downward. Okay. Let's see how it works, right? If I shift the threshold upward, okay, if I shift from 0.5 to 0.8, right? As you can see that the number, the size are decreasing. Because I'm pulling this ratio up, right? If I pull this ratio up, I only have 3 points left on the positive side. See? Okay? In the meanwhile, the number of negatives is increasing, right? In the different direction, if I move the ratio this way, as you can see that if I lower the ratio to 0.2, the number of positive increase, right? And the number of negative decrease, right? Okay? But whenever you switch the threshold, Tn, Fm, Tp, Ft would change, okay? And that would affect the measurement of accuracy, right? So usually when we use this traditional type of measurement, we are talking about the threshold at 0.5. Okay, that is the traditional way that we measure the accuracy. But that measurement is not. Today we will have a better way for measuring the accuracy, and it would be more useful when we are using probability model in business application. Okay. In order to demonstrate the new way, I have a simulator here. In today's folder, there's a simulation app called ENDPPSIM.R. You see that? Try to run the app. Can you run the app? Can you run the app? Anyone cannot run the app, please raise your hand. You can run the app, right? Okay, so it works fine for you, right? I would suggest you like open the app in the browser. It would be easier, okay, for you to operate. Okay, so this is the simulator, right? So this is not real. The data is not real. And here I kind of like simulate the distribution of the predicted probability. Okay. Again, the green is y equal to 0. The red one is y equal to 1, right? And here I simulate like 3,000 points of y equal to 0 and 1,000 points of y equal to 1. Okay? Yes?
What is the brown color?
Brown color?
The third color?
They are overlaid. These are because they are simulator, right? So the red color and yellow color, you can adjust they are normal distribution, right? So you can adjust their average and their standard deviation. Okay. So if you have a very good model, you have a model like this one, and then you actually predict all of the y equal to 1, the probability is higher than 0.5, right? And for all of the y equal to 0 point, you predict their probability is lower than 0.5. You have a very good model like this one. Okay, okay. But usually this is not the case, right? Usually you will see something like this. Right? You'll see something like well, right? Usually you will see something like this, right? The brown color is actually just the overlay of red and green. This is not true. This is simulator. I just want to show you the idea, right, about how it works. Okay, so usually this is the situation, right, and so you can set the distribution of predicted probability by yourself by this slider, right? You can set the distribution of the y equal to 0, y equal to 1, right? You can adjust them, and then you can set the threshold. Okay. If I set the threshold to 0, okay. If I set the threshold to 0, actually I can see that because if I set the threshold to 0, I will predict all of the point as 1, right? So if I predict all of the point as 1, my sensibility would always be 1, right? And the specificity is always 0. You can see that, right? According to the definition, right? Okay, because sensibility is actually the probability that I can predict you. When you actually 1, the probability that I can predict you as 1, right? But if I set the threshold as low as 0, I actually predict every point as 1, right? So if you were 1, I will always pick you out, right? But reversely, I will have a very bad specificity, right? Because my specificity will drop down to 0. See? In the other extreme, if I set the threshold here, right? So all of the point will be predicted as 0, right? So the specificity is very high, but sensibility would like drop down to 0, right? Okay? So so if I for every threshold, I can actually for every threshold here, I can move the threshold, right? So I can actually calculate the sensibility and specificity for every threshold, isn't it? Right? And in this plane, in the space of sensibility specificity, I will have when I move the threshold from 0 to 1, I will have a curve. Okay? And that curve is called ROC curve. Okay? That curve is called ROC curve. And the area under the curve basically is a general implication of the of how good your model can discriminate, can distinctively separate the two classes. Okay, the bigger the area here, the better that your model can separate the two. Okay. For example, if you have something like this. If your green and 0 distribution are not overlaid to each other, right? Then the area under the curve is equal to 1, right? Which means that the model can separate the two classes entirely, you know? And the more that they overlay with each other, the curve would like the area would like shrink. So right, okay, so measuring the area under the curve is a general way to measure how good a model can separate the two classes in all possible threshold. Which means that I do not set the threshold in the beginning, right? Actually, I scan all of the threshold, right, to get this curve, right? So the area is actually do not fix to a threshold, right? It is the general ability that, that that this model can separate the two classes, okay? So usually in modern data science, we prefer to use this AUC, the area under curve, to measure the the classifying capability, the ability that this model can separate the two different classes. Okay, and this is not related to threshold because all of the threshold has already been considered. Okay. So as I can say that the model's general discerning separating power, right? The AUC, what it means is actually general discerning power, separating power. Well, it has actually an operational definition, right? If you randomly, it means that when I randomly pick one point in green, pick one point in red, and the model can accurately separate them. Okay, that is basically the definition. But what we need to know is that I think this is more useful, right? So basically, this is how we do it. Okay, and in R. Let me stop the simulator and go back to the notebook. Okay. So in the code, I actually, this is for threshold equal to 0.5, right? So I can calculate so these metrics are the traditional metric, including accuracy, sensibility, specificity. Okay, so I write a function, so you can actually, if you give a confusion matrix, I can actually calculate the three things, right? So I define the function, so I can calculate the three things. Code is quite simple, quite easy, so you can try to do it by yourself. Now, this is for training, right? I can do the same thing for testing, right? Predict the testing. Now you need to give it the new data, right? New data is the TS, okay? And then again, you will have a vector of predictive probability, and you can see the distribution of this predictive probability by histogram. And this is for testing, right? And again, you can get the confusion measure by this, right? This is the true value, right? And this is the predictive value. See? Right? Predict value is equal to predict to larger than 0.5, isn't it? Right? So you will have a confusion matrix. This is the confusion matrix, and then you can like, actually you can compare the three accuracy metrics of training and testing, right? If you still remember how to use S-apply function, okay? So in the S-apply function, I have a confusion metric of training, I have a confusion metric of testing, and then I call the function, then I can compare the two, right? So as I told you that these metrics, they are based on a threshold of 0.5, and that is not very useful. Okay, for some business applications, so we introduced the idea about ROC and AUC, right? Okay, so and this is the way to calculate ROC and AUC. As you can see, it's very easy, right? Recently, there is a function called COLLC, okay, and this is the predicted value, right, for training, okay. This is the training data predicted probability, and this is the actual poor care in training data, right? So predicted probability, actual data, and then this argument is just to control whether you want to like make a plot, okay? If you do not make a plot, you will just simply return the area under curve. It will only return the area here, right? The area is always a number between 0 and 1 because the entire area is just 1, right? Okay. So if you have plot ROC equal to 4, it will actually return a value, okay? A value. And this is for testing, right? It's testing probability, and this is the testing Y. Then you have the ROC here, and then you can see that the area under curve for training and testing AUC are 0.77 and 0.79 respectively. Okay? So now we learn a few ways to measure the accuracy of a probability model, right? But we need to know how to use it in real business application, right? That's the topic of our next week's course, right? Now I need, please give me a few minutes. I need to explain your assignment this week, right? Your assignment this week is a little bit spatial, okay? I want you to go to an online training platform called EDX, okay? There's an online training platform called EDX, and there's a course called Analytic Age. This course is actually offered by MIT, the Massachusetts Institute of Technology, right? Actually, there's a business school inside MIT, right? It's a very famous business school called Sloan Business School, okay? This course is offered by Sloan University Business School, okay? I want you to like sign in to EDX. You need to sign in, right? So you can have an account, right? Okay, so after you sign in, you will have an account, then you go to this course, then you can view the course material, okay? Sign in to EDX, and then you can view the course material. And when you view the course material, you will see that there are a lot of units, okay? And one of the units is logistic regression. See that? Okay? One of the units is Unit 3, logistic regression. And I only want you to like follow what happened? It's broken. well, I don't know what happened, but do you get the same thing?
No, it was working before when I.
Yeah, it worked before, right? So something is broken here. So I want you to because it's online course, right? So there are some lecture, and there are some lecture within this. Let me see if I have. Oh, sorry. So you need to follow. I want you to just take this unit. Modeling expert, an introduction to logistic regression. Okay, there are a series of videos. Okay, and there are some quiz in between the videos. Okay, and the data that it used is actually the data that I'm giving you. The the diabetic data set, the pool care data set. Okay? In the beginning, you will explain how the data set come from, right? Actually, it is an insurance company, right? So you want to, it's very important for the company to know the care condition of diabetic patients. But I do not know their care condition. How can I know, right? So I randomly sample a few patients, 130 patients, okay? And I hired the expert to label these 130 patients because they are experts. So by looking at the medication record, you can label it. Okay, this one is good, that one is bad. This one is good, that one is bad. But experts are expensive, right? So they can only label a few sample data point, okay? So I can build a data. After I build the data with this sample data point, right? For example, I have a sample data point of 2 sample data. I build a model, and I have 2 million diabetic patients, right? Now with this model, I can actually predict the care condition, the probability of poor care of all of these 2 million diabetic patients. You get the idea, right? Okay. I sample some data, let expert to do the labeling, and then I use the label data to build a model. And then I want to use this model to predict the probability of poor care for each of my diabetic customer, okay? And then I can do something, right? That is the basic idea, okay? Now the reason that I want you to follow this one is because first of all, I want you to experience how the first class business school is teaching business analytics, okay? The way that they are using R, they're also using R, right? They're using R to do business analytics. And the way that they are doing it, okay? Try to do that. The second reason that I want you to do that is because logistic regression is kind of complicated, right? I'm afraid that only by listen to my explanation is not good enough, right? So you have a better chance to learn more about the logistic regression. The third thing is pay attention on the way that this MIT expert doing logistic regression, right? And you will see that the code that I give you is much, much better than the code that they are using in the class, okay? Because the class, this online class is designed in 3-4 years ago, and the code is kind of outdated, okay? So, And following that case, next week we will see how to apply that model to the real case. Okay? So I want you to like follow this. Try to finish the. Try to finish this unit. Okay? You don't need to do this. Okay? Don't need to do this, this, and this. Don't need to do that. Okay? Maybe you can like also take a look at this one. It's like just like a 3 minutes introduction. Okay? So it's a 3 minutes introduction, and then do this one, and all the 1, 2, 3. These three things you don't need to do. Okay? And there are some quiz inside the this unit, right? So I want you to like do the quiz and put it on a notebook and submit that notebook as your personal assignment this week. You get my point? There are a few quiz, right? And you do the quiz. Okay, you need to write code to do the quiz, of course. Okay, and then put the answer of the quiz on a notebook, right? Need the notebook, and like submit the notebook for your personal assignment this week. Get that? Okay, do it so we can start to do application on this case, exactly this case next week. Okay. Any question about the assignment? Okay, so that's all for this week. Okay, if no more question, I'll see you next week.